Hello everyone and welcome to another lecture. Today we will be talking one of the most important topics for our linear algebra course, and that is linear operators. So the first thing we ask is, what is an operator? The answer is, as you can guess, that operator is something that will operate on something, right? And in the notion of our Dirac notation or the bracket notation, we say that an operator is something that acts on a ket and returns another ket. That is, if you have some operator as omega and you have a ket, let's say v, so this v is an abstract ket vector. Remember, we are not using any representation right now, so we are just working in this abstract notation, and this is our operator, this omega. So it acts on v or ket v and it will return another ket. Let's call this v prime. So this is v prime. Okay, so sorry, that should be a pencil. Yeah. So this is what an operation, this is how an operation looks like. Here, again note that this is our operator. In some textbooks, they also use a hat, but let's not do that, especially in quantum mechanics book, whether when they try to distinguish variables from operators, they use a hat like this. But here we don't need this, so let's get rid of it. So this is our operator, and this is what it does. That is, it operates on something and it gives us another similar kind of object. That is, it operates on a ket and it will return us a ket. So what if now we ask that since our we have a counterpart for kets, that is, we also have bra vectors. So what happens with the bra? So let's take another bra vector. Let me choose another color. Yeah. So let's choose a bra vector w, and we choose another operator. Let's say an operator b, and this should give you another bra vector. And we will restrict to operators. Let me just write it down. We will discuss such operators that will keep us in our vector space. That is, we want to, let me write a partition over here. So we want to restrict ourselves in this to operators that takes a vector from some vector space v, let's say, and returns another vector in the same space. That is v. So we want those kind of operators that will take some vector from a vector space, it will operate on it, it will transform it, and the output, that is this v prime, will also lie in the same vector space. Now we will work in this abstract notation for a few bit, and then we will go to representations of these operators. So the next thing I want to assert today is that since we are dealing with linear operators and we have already defined what is an operator, so the next question comes, what is linearity in operator, or what is so linear in an operator, right? So let's try to answer that. Linearity will correspond to the following. Let's say you have an operator omega and you have a linear combination of a vector that's written as v is equals to, let's say, a1 and b2, just like this. So when you act on v with omega, this will be the following. Any operator that satisfies this is a linear operator. So this condition has to be fulfilled, or so to say satisfied, for an operator to be linear. Now let's take an example. Let's say this omega is represented with some matrix. I'm not writing down the elements explicitly, but this is a matrix and our vectors are some column vectors, right? Let's say that. If we do that, then you can easily see that this vector, we need to look at that because this was a1 and this was, a and b. So if I do this, then this is just this matrix over here with its elements, and here you have one column vector, and and here there is a scalar a, and there is a scalar b and the other elements. And you can see easily that this matrix over here will go on and act on this column vector and will give us another column vector, because the matrix multiplication is well defined here, and this scalar can be taken out, this a can be taken out, and similarly for this part as well. So this is one example of a linear operator, and this is for what we will see next is that this is a finite dimensional case. That is, whenever we can represent a linear operator with matrices, that will correspond to a finite dimensional case. When we are dealing with infinite dimensional case, that linear operator will correspond to a differential operator. So let me just write it down for now, and I will give you guys the reason a bit later. So this is a finite dimensional case. And by dimension, I mean the dimension of the vector space. Okay. If you recall from calculus, this derivative operator was a linear operator as well. Because if you had two functions and they're added together, let's take some arbitrary constants as well, a1 and a2, then you could write it as a1 df by dx plus a2 dg by dx. I mean, not by, that is the derivative, but that's how we pronounce it sometimes. So this is also a linear operator. That means this derivative operator is also linear. And this is an example of an infinite dimensional case. This is an example from an infinite dimensional case. And now I want to justify. By justify, I mean not mathematically rigorously, but just try to give a motivation on why we can represent the finite dimensional operators through a matrix representation, and for the infinite dimension, why we are calling it a derivative operator. So let's try to motivate our claims. Motivation for our claims. So, okay, here So first take the finite dimensional case. For a finite dimensional case, we can represent the vectors, that is the ket vectors, in we can think them in terms of the column matrices, right? And if you want, you can write down any vector, let's say v, in terms of v1 1, v2 2, v3 3, and so on. Let's say vn n. And for this finite dimensional case, I'm considering a n cross n. Not n cross n. It should be just n dimensions. That is an n dimensional space. Now, this is a vector, right? And this v1, v2, these are components, and I'm taking this 1, 2, 3 as the basis vectors. Or you can say orthonormal basis vectors, but I'm just calling them basis vector. So what will happen now is that if you want to act an operator omega upon v, because this is a linear operator, what will happen is that it will act on these basis vectors. Oops, sorry. Ultimately you have this thing, right? And here these terms, this one, oops, okay, I'll let it be. You can understand that this omega will fall under this brown circle, this one, they will get changed. So what will happen is that we will have this v1, and now we'll have 1 prime, we'll have v2, and we'll have 2 prime, and so on, vn n prime, right? So what is happening is that these bases are getting transformed, that is, their fate has changed. And if you write this whole thing as a, that is this one as v prime, not only you need to know how the basis changed, which okay, just let me write it down so that you can compare. Basis changed, this will correspond to n number of informations. And inside those bases, since this is a n-dimensional space, inside those bases you also have n number of rows, right? So for each and every basis vector, you need to know how these elements of these n rows are changing as well. So for each vector you need n information, and there are n basis vectors, right? So for each of them you need n number of information, that is those n rows. Okay, let me just write it down so that you can understand it better. So this basis change will correspond to this 1 prime, 2 prime, etc. And now how these elements are changing, elements inside a basis, that will also correspond to this n information. So what I'm saying is, let's say this is the first basis vector, and it has some, okay, let's just write it like this, or 0 or something like that, okay, and let's not take it to be 0, otherwise it will be a bit confusing. So it will have some elements here, over here, as columns. So these are my entries, and there are n of them, right? N of these entries. And when you multiply, or so to say, when you transform this, that is when it's 1 prime, when this is 1 prime, these dots are getting replaced by boxes, let's say. Okay, so here you need to have n amount of information, that is there are n rows, that is n elements, and you need to know how they got changed while the operation was performed with this omega operator. And you also have this 1 2 3 dot 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 up to n. So n times n is n square. So for a finite dimension with, for a finite n dimensional vector space, you actually need n square number of information to know what this omega does, to know what omega does to a vector, right? And all of these observations motivates us to represent omega in terms of matrix, right? Let me just demonstrate it in a simple manner. So let's call this demonstration. So let's say I have a vector v written in terms of the orthonormal basis vectors vi and I, like this, right? And now what do I want to do? I want to apply omega onto v, and I'm calling this v prime, let's say. So how to do it? Let's try to start from here. That is, we want to write this as omega times I. Sorry, not times I, but this is a summation where I is this index. And notice that I'm not writing down this I equals to 1 to n. This is not necessary because from the context it is clear that we are talking with finite dimensional vector space, so I'll just get rid of them. So this will be vi I, but this is a linear operator, right? So let me just write it down. The second line comes from linearity of the operator. Okay, now let's do it. I, and you write vi, and you write this whole thing together, omega I, right? Oops. So what we want to do now, you can write it as I prime as well if you want, but let's try to do it in another way so that we can actually motivate that these elements of this omega are just matrix element, that is, this omega itself can be represented by a matrix. So this line is coming from, that is, the second line is coming from the linearity of the omega operator. And now there are two ways that we can go about, but I'll just stick to the simpler one. That is, we'll first call this I primes defined as omega i's, that is, this I gets are getting transformed to some I prime, which corresponds to a change of basis when we think about it. That is, some operator is acting on this basis, and it is getting mapped to I prime. And this v prime over here, this is the changed vector after we apply this omega onto v, right? But we can still, since those I forms a basis for our vector space, we can still write them in terms of our initial basis vectors, right? But in such a case, we cannot take the same component, because you see these two vectors, that is this one and this one, that is just v and v prime, they are not the same, because when we apply this omega onto v, it goes to v prime. So that's why we'll write them as vi prime. So this is one thing that we are writing right now, and the other thing would be writing v prime in the original basis, that is in terms of I, as vi prime. The prime denotes that it's a component of the v prime, and just I. So let's use these two things and let's see what happens. Let's call it equation number 1, that is this one, and from 1, so let me just write again. From 1, you can see that v prime is just sum over I vi omega I, which can also be written as I vi I prime, right? Okay, so we want to see how these components change. So let's write v prime as sum over, oops, I forgot to give a sign sum over here. So instead of I, let's just take j, so that we don't get confused. And if you do that, then this will be vj prime j, right? And now comes the trick. The trick is we dot. Let me write it down so that you can understand better. So the trick. Dot both sides. Okay, let's call this equation 2. Both sides of equation 2 with bra of j. So let's try to see what happens if you do that. So again, let's switch back colors. So after dotting, by dotting I mean taking inner product. So this is j, v of j prime, this is bracket of j, you have sum over I over here, and you have v of I, and you have j and I prime, right? But this is what? This bracket of j is just delta jj, right? And this is just 1, so this will ultimately collapse into v of j prime, and here you have I, v of I, and here now expand this I prime, that is write it in terms of omega, right? Omega and the original thing. And if you just, since this is a number, and more organized way to write this would be I j omega I v of I, right? And finally you can write it like this, omega ji vi. This is similar to a matrix multiplication. Oops, it doesn't look very good, so let me just write it again. Matrix multiplication. So this is the thing that motivates us, that when there is a finite dimensional vector space, we can represent our operator, that is omegas, through matrices. And if you want to see how this thing looks, a very nice picture would be something like this. Let's say you have v1, v2. Remember, these are components, and here you have the matrix. Okay, let me go down a bit. Okay, so we had this j first and I second, so that actually tells you that it's the jth row and the ith column, right? So for here you will have 1 omega 1, in the down below you will have 2 omega 1, and so on. And here you will have n omega n. Here you will have 1 omega n. and so on and so forth. And here you will have, okay, there is a prime missing over here, sorry for that, and you will have v1, v2, v3, da 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 da. So from here you can also learn a new representation, that is the new notation, that the matrix elements of a linear operator can be given by, let's say, like this. So this is the bracket notation representation, this one. This is the bracket notation, but or Dirac notation representation of this linear operator, and this is the index notation, where this corresponds to the row and this corresponds to the column. So this is this completes our motivation for representing our operators in finite dimensional vector space as matrices. And for the infinite dimension, I'll just give a very short review or a short discussion. So whenever there is infinite dimension, what happens is that we have to know not a finite but infinite amount of information. Take for example, if you want to know behavior of this f of x, you have to know all the x's and all the f of x's, right? And this is similar to finding information about an infinite dimensional space, and it is similar to this functions, that is let's say I'm taking x from all the real numbers, that is from minus infinity to plus infinity or something like that, and you have to know each and every point, and between 2 points you can have infinitely many points. So that's like knowing knowing infinite amount of information to know everything about this pair, that is x and f of x, right? And that's why here you can have linear operators like this differential operators. You also know that integrations are also linear operators as well. So these are the examples, and this is what this is very non-rigorous motivation for why you want to deal with infinite dimension with this kind of linear operators. But for our next discussions, we will be restricting ourselves to these finite dimensions, where we can safely take these operators to be such that we can represent it by a matrix. And here, and there is an important remark, okay, let me write it down. An important remark is that the elements of the matrix elements of the operators are basis dependent. So this is an important remark to keep in mind, and hopefully we'll discuss more when we talk about these linear operators in the next lectures. So until then, stay safe and thank you.